So this should be the figure that we're going to connect. CR1, everybody there in those lab books?
Experiment.
CR, which is past timers, I think. So we're in the CR section. First lab, y'all get out y'all's lab procedures and make sure I'm going over the right circuit. CR1 is the one we're supposed to do, right? Now, this is a true reverser, so this would be the circuit that this guy here would represent. So here's the two relays. One of them you would call what? Forward. The other one you would call reverse, right? Here's the overloads. So these are the overload sensors. And what's the overload? What do we use overloads for?
Motors. Safety.
Not all motors. What's their function in life?
Change the
Yeah, but why? Why do we need overloads on motors when we have fuses? Why can't I just use a fuse to protect a motor? So nobody in this class, as much as we talk about overloads, nobody in this class knows why we use overloads on motors. What's the full load current, or what's the full load current on a motor? What's that rating? It's rated in amps. What does that mean to you? These are going to be on the next test. What does that mean? What does that mean? If I go over and look at that one and it says 1.2 amps, what does that mean to me?
It's how much ampage that thing's going to draw at its rated horsepower.
Running at its right. So this is how much it'll run when it's running, not when it's starting, when it's running. Now the problem is that when we start a motor, if I was to look at a current curve, it would come up and do this, and then it would drop down and it would level off. And what did I use? Just like your car. You're sitting at a red light. When do you get the best gas mileage out of your car?
At high speeds, cruising about 40.
At a constant speed, right? When do you get the worst gas mileage out of your car? When you're doing stop and go, right? Stop and go. Why?
It takes more gas
To get it started. It takes more gas to get it in motion than it does to run it when it is in motion. So what we have to do with this thing here, rule of thumb is 6 to 8 amps. So let's just say this right here is 1 amp. And this up here would be 8 amps. What am I going to fuse this motor at? What's my overcurrent protection device going to be fused at?
amps.
More than 8 amps. At least 125%. At least. Right? Because that's depending on everything being correct. Okay, so what if the motor don't start and I fuse it at 10 amps? What if the motor don't start? It'll burn up the motor. Because we've got it fused for 10 amps and it's drawing 8 amps. So when we fuse a motor, we have to size the fuse that would allow the motor to start. You understand that? But what if it don't start? Well, we got to have some type of protection device that would allow the motor to start. But if it don't start, it would kick out the circuit. And these are overloads. So overloads are going to detect if the motor does not start or if it does what? Stalls. So overloads allow a certain amount of current to flow over a short period of time. That's what overloads do. So almost every motor is going to have an overload in it. External overloads are usually for dual voltage motors. So most motors that you're gonna run in the industry are probably dual voltage motors, which means they have the ability to run on a high voltage and they have the ability to run on a low voltage. But you have to rewire the motor, right? And some of y'all got that section. The problem is overloads don't sense voltage. What does overload sense? Current. So that means if I've got a certain horsepower motor and at high voltage it draws 1 amp, then at low voltage it'll probably draw about half an amp, which instead of this being 5 amps right here, now it's going to be 4. So what that means is if I've got a dual voltage motor, that means these overloads are going to have to be changed out if I run it on low voltage. I'm going to use a higher current rating. If I run it on high voltage, I'm going to be using a lower current rating. And that's why I'm going to come over here and we look at our chart, right? Remember when we chose that overload? We use the full load current, but that's compensated for by the overloads. Y'all understand that? So we have a dual voltage motor, so that means our motor needs to have overloads. And we're using heater overloads. These are the cheapest. And they've been used for years. So that means if you don't have a perfectly new insulation, then you're going to run into heater overloads. Which means if you take that same relay and you move it on a low voltage motor, you're going to have to change the heater dial. Because if you don't, right, you understand. If you put low voltage and then you run it at high voltage, you can burn the motor up. Because now the things are looking for 10 amps and you're only pulling 4, right? Understand that. So overloads are used for dual, and every motor's got them in there somewhere. Most of your house motors are internal. So I came over here and I pulled this little stator out right here out of an AC motor. And by the way, we are going to move all this over here. If I can find it. And right here at the top, we got this little old red thing right here. Right here. What do you think that is?
It's hard to see with the light, like the light.
Oh yeah, y'all somebody go turn off the first two on the left. No.
Well, it's still.
I'm sorry, they're staggered. I'm sorry.
Actually, have a glare from that thing. Yeah, it's actually the angle of the light from the projection.
Well, I'm gonna pass it around anyway. I'm gonna pass the stat around anyway.
Internal overload.
This is the internal overload. So this has an internal overload on it. This guy here automatically resets. So that's what I'm saying. If you're working on like an air conditioner or something in a house and the motor's not running, don't get your hands in there, because if it's kicked this overload, as soon as it cools down, what's it gonna do? It's gonna take off. These overloads, these industry overloads, have to be reset. So the overloads themselves are gonna have a reset button on them. This is an electronic overload. This is an electronic overload. So you got this little dial right here. You can set different currents on it. But this is one of our worst nightmares, because why? Yeah, you got these guys out there that's working on incentives and they're getting paid by how much they put out, and they'll go out there and turn the overload out on it, and then the motor burns off and they're down for a week. So they got incentive for 1 week and now they're out of work for a week and they didn't get any incentive, right? That was a big problem we had at US Steel, because everybody was paid on incentive. That means the more production you put out, the more money you got. And we, even in maintenance, we got a certain percentage because we kept everything working. So I see him jump out fuses with welding rods because they kept blowing. And then they burned stuff up and they wondered why.
So they put a welding rod in between where the fuse goes?
Yeah. No, it's not. That's a true story. And sometimes they would do stuff like that on purpose because if they had to go down anyway, so they had a downturn. And what sometimes they realized, if they could get it to the downturn, they wouldn't lose any money. But if they went down during an active shift, they would lose that money. So sometimes they'd burn stuff up on purpose. I saw them run fire hoses on the side of number 8 blast furnace for 2 weeks or more because it would have cost them more money. And this was before, no, number 7. They was getting a new blast furnace, number 8 blast furnace, the brand new one that they've already tore down over there. But they wanted to keep number 7 running. If they were to take it offline and reline it, then they would have been out of business for a long time. So they ran fire hoses on that thing on the side of it for like a month, constant, just to keep it to make it till they got number 8 up and running. So that's true story too. Now ours do not have, and what's this symbol right here for?
They're mechanically interconnected.
Yeah, we don't have mechanical interlocks on ours, and I passed that around the other day, right? And another thing that we're going to use, we don't have any true reverser contactors or motor starters. So what we're going to do is we're going to use 2 standard motor starters. So what that means is we're not going to connect this wire right here. So you need to go ahead and make these corrections in your book. There's several more in here, but every one of them we're going to have to modify no matter how they are to take out this common connection, which would be for a true motor reversing starter. And we're going to use 2 just regular motor starters. And so we'll have this regular here. Of course, this symbol on the right-hand side, this is the symbol for the overload. For the reverser, and it's a symbol of overload for the forward. So everybody okay? Okay. Now, what's the biggest problem we're going to have? So what we're going to do, and this is going to be in your lab book, is you're going to wire the control circuit first before you even wire up the motor. Then we'll come in and we'll check to see if the control circuit works. Because if we have a problem with control, if somehow your forward and reverse come in at the same time, this is going to create a short circuit. You're going to directly connect L1 to L3 without anything in there. So what we're going to do is make sure that these contactors work correctly before we hook up the motor. Right? Everybody understand? So I don't know if I've got the actual white diagram for the, now this is the control circuit, but I can draw it. And then what you're going to find out is the wiring for the motor is in the wiring diagram. Oh, I can get to my black now. No, I can't. Dang it. Oh, I'll get to this is good too. So what we got is coming from our 3-phase, which is not L1, L2 for our control circuit. This is L1, L2, L3 on the 3-phase on your disconnect. So this is going to come down, and it's going to go to your forward controller. I don't know what I'm doing, guys. Sorry. So if you don't know what you're doing, we're in trouble, right? I know what I'm doing in the story line. This is not the control circuit. This is the power circuit. So you got both of them in your book, right? In your lab book. You should have both of them with this circuit here. Is that true?
Mm-hmm. It says with the motor. Yeah, we got it.
Yeah. So this is the power circuit. And then over here, this would be forward. So that's going to be controlled. These are going to be controlled by your ELF controller, right? And then over here, we're going to tap off these.
And I'm going to jump over these guys, even though that's not legal, but I just want to make sure you understand they don't connect. And then we'll bring these down to our reversing controller. I think I can. I got 1, 2. I need 3, don't I? Okay. And these go straight across. So what we do is we don't reverse them on the top, we reverse them on the bottom, right? So this is called L1. So let's come back and erase the F and I'm going to put the actual contact control on the right. So this would be F, and this would be R. Now follow me so far. Okay. This is going to be on your connection on your actual controller. They're going to call this L1, L2, L3, and this will be called L1, L2, L3. Okay. Yes or no? Then what we, huh?
It's gonna call on the relay.
On the relay. That's the way the contacts are actually labeled. They might have numbers beside them, but they're also labeled F on our contactor. This one don't have it. You would have to look it up. But we'll go over there and look at our contactor in a minute. Now on the bottom, we have the overload sensors, which controls the contact that's over in the control circuit. And this is the symbol of an overload sensor. And then down here, we're going to have 3 terminals, which are going to be labeled T1, T2, T3, T1, T2, T3. Because y'all understand that? Okay. Everybody okay so far?
Same, basically.
Yeah, they are. They're not basically, they are, but it's 2 different relays. So here I've got my F in my control circuit and I got my R. So this guy is not only controlling some internal contact, auxiliary contacts in the control circuit, they also have contacts in the power circuit. So when we talk about contact, so what is a control relay?
Don't you have that labeled backwards? But you don't have it reversed on the bottom.
I hadn't wired the motor. I hadn't wired it up. This is coming out of the contactor. These are not reversed in the contactor. We're going to have to wire it because there's no white circle. So that's a good point. This is the actual contactor. So if I was to come up here,
Well, I mean, you labeled as T, which is the motor connection.
yes.
So if that was labeled it's going in the same direction either way.
No, you're not listening to me. This is the contactor right here. So this is the contactor. So what I've got is I've got these screws on the bottom of the contactor. These are not wired internal. I've got to wire them. So these are the screws. So you're wait till I get through, Kevin, and you'll see what we're doing. So what is a control relay? That's on. It's going to be on test 3. What is a control relay? So we got control relays, we got contactors, and we got magnetic motor circuits.
It's an electrically controlled switch.
Well, so is a contactor, and so is a motor circuit.
Only in the control circuit.
A control relay only has contacts in the control circuit. It has no contacts in the power circuit. What is a contact? It is a relay that can have contacts in the control circuit, but it definitely has contacts in the power circuit. It's a relay that is designed to control stuff in the power circuit, but it does not have overloads. So what's a magnetic motor circuit? It's a relay that can have auxiliary contacts in the control circuit,
But it definitely has contacts in the power circuit, and it includes overloads. So that's the big deal. Got a contactor run the motor. As long as it don't require overloads. So you're gonna run into contactors all. So this little old contactor we have up here that runs an air conditioning system. So what I'm gonna do is I'm gonna come down here and I'm gonna wire my motor. So this is the symbol for the motor. Let me switch back to my color. This is my symbol for a 3-phase motor. It's gonna be round and gonna have 3. So I'm gonna take this one on this relay and I'm gonna bring them straight down. When I come up here and wire this one, I'm going to take T1 and I'm going to hook it up to T3. I'm going to take T2 and I'm going to hook it up to T2 and I'm going to take T3 and I'm going to hook it up to T1. Now you understand, Kevin? So these two motor starters, they're identical. It's you have to wire the watt. So when the F comes in, L1 goes to T1, L2 goes to T2, L3 goes to T3. When the reverse comes in, then T1 goes to T1 goes to T3, T2 goes to T2, and then if we call these motors, and that's what's probably getting you confused. T1 is going to go to T3 on this one. T2 of this one is going to go to T2 on that one. T3 on this one is going to go to T1. So when the forward is conducting in L1, L2, L3, when the reverse comes in, L3, L2, L1. And that's the way we do it. And this is your power circuit. Now, I mean your power circuit. And it's drawn as a wiring diagram. So normally, if you look at the thing, not only does it have your control circuit, not only does it have your reversing circuit in there, it's also, the motor circuit, it's also got your control circuit. And we don't need to even pay attention to the control circuit. All we need to pay attention to is the wiring circuit, the wiring of the motor on that side, right? Makes sense? Everybody okay? Question?
Well, here's why I was asking that question. I understand how you can wire it like that, but now you have two wires, and we always label them as T1, T2, and T3. Wires going from out of the OLO into the motor.
Yeah.
Now you have a wire labeled T3 and T1 connected.
I don't have a wire. I don't have any wires like that. These are manufacturer numbers that's on. These are manufacturer numbers that's on the relay. These are not wire numbers. This might be wire 53, 52, 50. Yeah, they might be.
Tower. I'm just going by my experience and why because now they're electrically the same, but they're labeled different to two different places.
But you're getting wire numbers confused with manufacturing. You understand?
Well, I mean, that's how we label them. That's where
These are reversing, or these are reversing contactors?
Yeah, and often we would reverse it on top.
No, you never reverse it. That's not industry standard. It's not industry standard. Reversing it. Now, the way you do it at your plant, then that's up to you and your manager. What we do is we use the reverse on the bottom. And this is industry standard. So in this book right here, you'll never see anything reversed on the top. Now, what you're thinking about is you might be thinking about this guy right here. This is a reversing contact. We are not using a reversing contact.
Right. Yeah, that one is wired.
It's swapped. It's swapped inside. It's swapped between the overloads. So this guy is wired for you. Our problem is we don't have reversing starters. We have two motor starters.
Okay, so I'm with you.
Now you're with me. So yeah, you're
probably
probably
singular overload as opposed to two separate.
right. Two single overload. This guy has a single overload, and it's also the reverse is on the bottom. If you looked at the wire diagram for that one, you see it's reversed on the bottom.
Right.
You know, that way it's so easy to get the top, want this, that one, that one, that one, that one, that one. So I understand your question. Man. So you're dealing with one relay, we're dealing with what?
Two.
Two.
So we would always have them mechanically interconnected as well.
Yeah, we do too. But even that one right there is not mechanically interlocked. So if you can take the two push button, some people call them test to push, but we call them mechanical overrides. So almost all these relays will have this little black button on the top, which you can do what? You can force it in for troubleshooting. Well, if it had a mechanical interlock, I wouldn't be able to do that. So this would give people problems because I just created a short circuit between, even on this one. And the problem is that short circuit's on the top of the overloads and it's not on the bottom of it. So you understand that, Kevin? You okay?
We're good.
So everybody okay? Does this make sense? So this is the way we're going to have to wire a circuit. And it's good too that you understand that swap, right? So this is actually a little better in my opinion because now you understand that swap and how it has to be wired inside that thing. And the problem we have is you can buy these as a unit, but if the overload goes out, you're probably not going to replace the whole thing. You're just going to replace the overload. Now it's up to you to do what? To wire the overload correctly. So learning in here would be best. And even if the relays go out and the overload's okay, if one of your relay goes out, then it's up to you to come in and wire it correctly, right? And if you don't wire it correctly on the bottom, then you end up with a short circuit, right? And we got to prevent these two things from coming in at the same time. So that's what these electrical interlocks, which everybody gets messed up on. Because we end up with a lot of stuff with the same number because the two relays are exactly the same. So these contacts down here will have the same number as these contacts down here. This contact right here will use the same numbers as this contact right here, but these are on different relays. So you got to run this one from your forward switch over to your reverse contactor, right? You understand that? And you can tell as soon as somebody's got it wrong. So what would happen if I use the forward up there? Well, what would happen is you press the start button. This energizes, this opens. As soon as it opens, right, this closes, this energizes. So your relays are just sit there going to buzz at you, which is the way old doorbells used to work. It used to work on that exact same principle. Had a little solenoid in there. It had a contact on it. When you press the button, it would go, it would break the circuit, come back, make the circuit. And some of the old bells might still work. So that's the biggest problem some of us have. Another thing that we have, I need to find at one of the motor starters. I thought I had. Did I pass the motor starter around? I wasn't recording it, guys. I guess I need to go back and. So we'll go ahead and sign these numbers right now. So we're going to get rid of this wire right here, right? Because this is not what we have. Then we're going to bring this over. We're going to have another overload right here. This is going to be 10. This is going to be 9. These are manufacturer numbers. You don't see this connection. This is internal. This is going to be 10. This is going to be 9. Oops, Rich. This is going to be 9. That's what most people make a mistake right there. So you're not connecting right here. You're connecting right there, right? And then on our overloads, this is going to be 7. This is going to be 8. This is going to be 7. This is going to be 8. Let me see. Let me look real quick. Let me pause this. And we got everything but the stop button, right? One of your challenges is going to be to not exceed 2 connections to any point. But notice 5 does not have to connect to 8. 5 could also connect to 7 over here, right? Understand? Big problem. We got a 7 there, we got a 7 here, we got a 6 there, we got a 6 there, we got a 7 up there. So you got to remember what number you're looking for on what device, right? Because these are manufacturer numbers. The biggest problem we have, of course, is people not doing the cross couple. They forget which relay is forward and which relay is reverse. Okay. So if you want to get a piece of masking tape and label them, that's fine. Don't write on the don't write on the relays. So I've wired this up. Took me about 15 minutes.